Welcome to Thursday of week 8. We're doing geometry today. And the warm-up is trying to figure out if you started with 14,000 square feet and took away 2 rectangles of a certain size, how much space is left over?
Okay. I think I got it.
Okay, tell me what you did and I will copy it so everyone can see.
I multiply 65 feet by 80. And I got 5,200.
5,200, okay.
And then I multiply 50 by 95.
Okay,
And I got 4,750.
okay.
I add the two totals and it gave me 9,950. And I take away that amount for the 14,000.
Okay. Is that either what you two did or were thinking about doing?
Where did it? It left us with 4,050. 4,050.
Okay, I've left some space for the labels. This is square feet,
Yeah,
whereas each of the sides is just feet. And again, feet is something you could measure with a tape measure. Like it's just, I'm going across a line, it's a distance I could jog. Whereas square feet means I'm putting little squares on, like I'm putting tile on the floor of a kitchen or bathroom. So it's a different kind of thing. It's not a distance anymore, it's an area. How many squares you would need to cover the area.
4,050 square feet.
So you could do all of this without labeling things as you go. But just for the sake of completeness, I'm going to remind myself that these are all feet times feet is square feet. Some people like using this notation, which is sort of just a cleverness. Look, an exponent of 2 means squared, so we're gonna make it square feet. Haha, we're smart. But it's also more than that, because if I'm taking 65 feet and multiplying it by 80 feet, it is sort of like I'm having the word feet times the word feet. So the fact that this is saying the word foot times itself, yeah, that is actually what's happening. So you can think about that either way. But when I'm lecturing, I will normally write square feet that way because it's a little more clear. Okay, that looks perfect. Okay, now that we've had our brain warm up, then we talked about perimeter a long time ago. We just add up the edges. If you remember, my advice was that people sometimes miss this on the test. And you might say, how could anyone get this wrong? All I have to do is go on my calculator and say 9 plus 5 plus, whoops, my plus is not working. Plus 5 plus 4, what else is here? 9, 5, 4, 6, and 8. You could get it wrong if your calculator is. Okay, so ta-da, that's 32. But people do get these wrong. And the reason is that your brain shuts down on a test for panicking. It happens to everyone. And maybe you forget a side. You don't include, for example, the 8. Or maybe you double count a side. Maybe you do 9 again, because you forgot you already included it. So in order to avoid those careless mistakes, what I like doing is marking kind of which corner I'm starting with and which direction I'm going. And then I can double check. Yeah, 9, 9 and 5 and 4, 9 and 5, 4, 6 and 8. 6 and 8, and that's all, and I'm back to where I started, right? So just a little bit of extra work, but it keeps you from making a careless mistake. Area for rectangles, we already talked about. We just did that, length times width with the rooms in the moon base. And triangles we talked about. So let's go over how that works. So you have some papers in front of you. I don't think we actually had these last time. Betty doesn't have the paper, I'm sorry, but I'm gonna move over to here where she can kind of see this one. Okay, so we're starting with the top picture on the screen now. This is like an origami test. So try and fold your paper diagonally from one corner to the opposite corner. It's a little tricky because we're not used to folding like that. Try and do this fold. Actually, can help with you.
I can't get it either.
There's you on there. Okay. So my challenge to you is to convince me that these two triangles are both half of the rectangle. They are. That's pretty obvious. Can you put them to words why they are?
You should basically fold it and then unfold it and put it together.
But maybe I didn't fold it in half.
Yeah.
How do we know that this picture, this top one on the slide, is that half?
It's just a piece of it. It's basically half big.
If I took a scissors and cut where I folded, then I'd say, look, and this one fits on top of the other one, they're the same size. You could also argue it that if I took this and I turned it upside down, I can't tell. So they have to be the same, because when I flip it, it looks the same.
They're both the same.
Okay. Are you okay with this, Betty, even though you don't have a paper with you?
I know that one, yes.
Okay, so now we're gonna do a harder one. Take another paper. And you're gonna pinch it somewhere on the top. That's not the middle, because that makes it look too easy. And then fold from there down to the bottom corners. So now we have the picture in the middle of the slide. We have a triangle and the top is no longer conveniently at one of the top corners. It's somewhere else.
So I got it.
Yes. Oops. Oh, okay, so here's yours. So this one is less obvious. How would you prove that this triangle is half of the whole thing? Or on the slide, the green triangle is half of the whole rectangle?
It looks as, they're both the same on one, on that top one. Cause you're putting that one, you just move that little, you know, that line on the edge here, this one this way, you can move that way and move that other triangle over here.
Yeah, so this is no longer as easy. I can't just say I flip it and it doesn't change. But if I took my scissors and cut either of these top bits and then slid it to the other side,
It would make sense.
now if I turn it over, I can't tell.
They're about the same.
Yeah, so that means that this green big triangle has to be half of the whole thing we started with. So on the slide, I can say this green one, I can just putting half over here. And that makes the other one,
Yeah,
so,
it makes the same. It's the same.
like that, I can take this piece and move it over so that the green is.
It's this trickery.
Yeah. Okay, now we're gonna move on to other shapes. So one of them we just did. This thing that looks sort of like a square that an elephant sat on is called a parallelogram. Because the lines that are top and bottom are parallel with each other, like railroad tracks. Let's highlight those in one color. And then the lines that are kind of diagonal are also parallel with each other like railroad tracks, but going in different directions. So that's why they call it a parallelogram. Okay. And we just made that, right? When we took our triangle that was half of a rectangle,
Was it parallel?
did that, we made a parallelogram.
Yeah.
So that means that the area of a parallelogram is the same as the area of the rectangle that it started life as before we cut it apart. Which is interesting, because the area of this is its length times width.
Yeah.
So where is that on the parallelogram? And if I move this over here to get the original.
Yeah, it turns into a block.
So I'm gonna put these off to the side for now. So the length. Is here,
Exactly.
the
Do
width
you
is
like my
here,
drawing?
or the other way around, we can disagree of which is length and width, which is width. So when I rearrange that. Then I need to measure the inside of this shape. It's not the diagonals that matter. I don't have to try and measure that diagonal at all. It's this up and down length that matters, because that used to be a side of a rectangle, whereas the diagonal wasn't. It was inside, and inside doesn't matter for rectangles, only outsides.
Cool.
So this is the first shape we've seen where one of the things that you need to do is measure the inside of it. Which is a little strange. The last shape is called a trapezoid. Trapezoids can seem a little tricky. You don't have to remember anything about trapezoids. Because anytime anyone gives you a trapezoid on a test like GRE, then or GED, then you can just slice it and make two triangles out of it and use what we know about triangles. Or you could slice it a different way and make three triangles out of it or something like that. Usually one of these goes straight up and down. And so you can cut this apart into things you already know. But if you
Is
don't,
that, sorry, is that one of the question on the test?
they might ask you about trapezoid area. They're going to give you on the test. GED info, the formula sheet. And the area of a trapezoid is here.
Okay,
They could ask you about that, but now I'm gonna teach you what this means.
okay,
Look, it's familiar. So what is that formula about? What it's saying is that to find out the area of this shape, so what I'm going to do is take two triangles. And I'm gonna put one on top of the other. And I'm going to kind of cut diagonally. Okay, so this is the trapezoid that I'm starting with. And now I'm kind of stuck. Because what we did for the triangle was say, how was it originally a rectangle? Because rectangles I know. And for the parallelogram, we said, how can we make it a rectangle? Because rectangles we know. But this one, I don't know how to make it a rectangle. With two kind of arbitrary bits chopped off, I'm not sure what rectangle this used to be. So I need a different trick. So my other trick is I'm gonna photocopy this shape. And then one of them I flip over. And then when I put them together, now I have a parallelogram. Doesn't matter which way I do it.
Cool.
So I can turn a trapezoid into a parallelogram. Okay, now let's look more carefully at the screen. Okay, so. What am I gonna do? I'm gonna put this one back. Okay, so I started with my red trapezoid. I photocopied it and I put the yellow photocopy next to it. In order to find the area of this bigger parallelogram, then I need to do two things. I need the length, whoops, let's make that small. The length all the way across the bottom. And I need the height. Again, because this parallelogram used to be a square, if we took this part and moved it over here. So I need these two things, but that's not what they gave me when they give me a problem like this. They will give me the height, I'm okay with that. But instead of the length, they will say just of the red one. What is its top and what is its bottom? So what they will actually give you on a test, if they give you one of these problems, is they will say, here is the height, the top side, and the bottom side. Are you with me so far?
Mhm.
So now
Yeah.
roll up a tiny bit, and I say that this was, oops. That this was the bottom. And this bit here, that's the same as what used to be the top on the old one before I photocopied it, right?
Yeah.
So when I add together the bottom plus the top, that gives me this length that I want across the whole bottom. So the area of my big shape here is gonna be the height times the top plus the bottom.
And they want the formula too?
Yeah, they're not gonna ask you to derive the formula like this, but they're gonna give you the formula and I want you to understand where it came from. I'm not done though, because that is the whole area of this big thing. And that's twice as big as we want. Because remember, we started by photocopying what they really gave us.
Yeah.
Since I got something that's twice as big because I photocopied it, then my last step is going to be a divide by 2. So that's how you get the area of a trapezoid. You have to take the top and bottom and add them up. Multiply that by the height and divide by 2. So that's what they're showing you on the formula sheet here. 1/2 times the height. And then they're saying B1 plus B2, base 1 plus base 2. It's just a different way of naming the top and bottom edges. So now you know where that comes from. That's usually faster than trying to chop this shape up into triangles. And using the triangle formula on one and using the triangle formula again on the other and then adding them back up. So if you can practice with the formula, it will save you some time.
Cool.
Okay, let's do some examples now that we've seen where these come from. So the point of all of this was not again that you'll be asked to derive these yourself. They will give them to you on the formula sheet. But I want them not to be mysterious. It's not like some ancient Greek guy, had some divine revelation about formulas. No, they're just things you get by chopping up rectangles, moving them around.
Cool.
So here's all of the formulas. Let's review them over one last time. A square is base times height, and the same with a rectangle. The triangle is half of that, because if I started with a rectangle, I can cut it in two, and the triangle is half of that.
Yeah.
The parallelogram is the same as that, base times height. The only trick is that the height is inside, and that's again because I could take this triangle piece and move it over here, and I get a rectangle, which is base times height. And then the trapezoid, we just did the last, and that's where you're gonna add the top and bottom, multiply by the height, and then divide by 2. So here's a bunch of shapes. We're going to pretend that each square is just 1 foot to be easy. So what's the area of this dark red triangle to start with? This one.
Let's see, it's 1 foot, right?
Yep, each square is 1 foot.
It's like about 6 square feet.
And how did you get 6?
So what do you see? Look at, there's 12 squares, but then again, I'm looking at it wrong, so it's like 12 square foot, but you have to multiply it by, yeah, 12 square feet. I divided it up and it was like 6.
So first you notice that the whole thing is 12. And maybe you just counted them and there's
Yeah.
12. Or maybe you didn't count them, but instead you said that this is 3 times 4 is 12.
Yeah,
Either way works.
Yeah.
And then you say that the triangle is half of that.
yeah.
So half of 12 is 6.
Yeah.
So this is 6 square feet. Everyone happy with that?
Yeah,
Yes.
Yes. Okay, how about the blue one? How big is the blue triangle?
I don't know. That's kinda, I mean,
And do the same thing. Can you copy what he did, Jody? First, tell me how big this whole rectangle is that's surrounding the blue.
I don't know, but that does look big.
I'll count it. How many squares are in it? Either do length times width or just count them.
there's 6, right, there's 3, and the other side is 2.
Again, on the GED, you'll have a calculator, so even if your times tables are rusty, you can do 6 times 3 is 18, or just count them all. And we get that the rectangle is 18 square feet. So how much is the triangle going to be?
should we do half of that?
Yep,
Yes,
so half of 18,
It's 9.
9 square feet. Ta-da, so don't make it harder than it is.
Yeah.
Okay, now let's do this kind of burgundy parallelogram.
It looks like it's like you miss. Looks like you're chopping up some stuff here. Looks like you're smaller than this. But it looks like it's the same.
So what is the length of the bottom of this one?
It's 4,
Or, this part doesn't count though.
3, sorry, 3, you're right,
So this is 3, and then how tall is it?
3,
3, so 3 times 3 is 9.
9,
It's actually the same size as the triangle we just did. And you can kind of see that if we took this part here and cut it off
Yeah.
and moved it over here, then this box would be 3 times 3 is 9. Does that make sense?
Yeah, I saw that, I just wanted to see if anybody else sees that, 'cause I saw that.
I made it
so
more,
it's gonna be half a 9,
no, just 9,
just 9,
as it takes up. Let's look at this one too.
hmm.
So so with this kind of orangey one, then
There's 5,
1, 2, 3, 4, it's 5 on the bottom. And the height is 3,
3,
so 5 times 3 is 15. And if we grabbed, it doesn't come apart, does it? No, I wasn't that fancy. So if we grabbed the this part here and moved it over here. So now it's gone and not there anymore. Then this is 15, right? 3 times 5.
Right.
It's half of 15, it just is 15. And then the last and most complicated, so what's the height of this trapezoid? 1, 2, 3, 4. The top is 1, the bottom is 5.
5,
So we're gonna go 4 times 1 plus 5. And then we're all done, divide it by 2. So 4 times 6 is 24. 24 divided by 2 brings me down to 12 square feet.
Interesting,
So that's how to do that.
that's an interesting concept, I did not know how to do that.
Does it look like this shape is just a little bit bigger than that shape? Or was a little bigger than not?
Pretty much, but it was only like only 3 square feet difference,
Yeah, it's not that different.
but similar.
Not all of these our brains are good at. Most people can't look at the this one and immediately tell that it's bigger than that one.
Yeah.
Right, so our brains are just good at certain things and not other things.
So just looking at it differently, yeah.
Okay, well, that's all there is about the geometry for Math B. There's a lot more in Math C. If we again go to the what comes next. Then you get some interesting stuff here, and you get some interesting stuff here, and the area puzzles are the fun things. If we had more time, we can talk about temperature, but I sort of just saved that for the readiness test, because it's so
Yeah.
easy. And we could have talked about that when we talked about plugging things into formulas earlier, but I don't think we picked that one.
Yeah.
Angles we need to do something with. And is there an angles coming up in the, yeah, in the geometry ones? Oh, I'm backwards, that's why I'm confused. Measurement units was the short topic. We somehow skipped over that and are doing area today. Oh, well, that's fine, we're doing things out of order. But it is 7, let's take a break. And then we'll come back and do our measurement units like we should have been.
Right, yeah. I'm gonna get.
Oops, I messed up. Yeah, we're doing measurements like we should have the first half class, but we'll just have to switch, it's okay.
That's okay.
So Jack and Jill are older, stronger, healed from various injuries. They need to bring home 5 gallons of water, not more and not less. Jack has a 7 gallon bucket, so this big bucket, and Jill has a 4 gallon. And the well is far away, so they want to make only one trip. So how can they pour water back and forth between their buckets? So that Jack's big bucket has 5 gallons of water in it on the trip home.
Okay. There you go. Got one for the new person, he can have two.
Okay,
And the other one for the security guard,
okay.
it's on the side.
And make more if you want, or turn it off.
I just turn it off.
Okay,
Go ahead.
yeah, so how are we gonna use the buckets? We can fill up 7, we can fill up 4, we can pour water from one bucket into another bucket.
So you need to bring home 5 gallons of water, not more or less.
Right,
And so Jack has 7 gallon bucket and Jill has a 4 gallon bucket.
So they need only 5 gallons.
Right.
They can have the 7 gallons, and they can help each other with 5 gallons of water.
if they could fill up 7 all the way, but then they're carrying too much. Right, they're trying to make some giant stew or something where they want just 5 gallons. And that's what their parents sent them to do.
Hmm,
If you haven't seen this before, you pour water back and forth. For example, if I filled up the 7 gallon bucket, so I have 7 gallons of water. And then I took it and poured it into the 4 gallon bucket. Until the 4 gallon bucket was full, and then I stopped, how much would be left in the 7 gallon?
1 gallon.
No,
Oh, be like how much? 6 gallons?
I had 7 and I put 4 in here, so
So still have 3 left.
I still have 3 in the bucket.
3.
So if the goal was 3, I could make 3 exactly by pouring things back and forth. So you need something like that to
Okay.
use the buckets together to make 5 instead of 3.
So I'll tell him like on my trip on that. So if you were saying 5 gallons on the bring back home, right?
That's the goal, to make 5 gallons in the 7 gallon bucket.
Which remaining 3, you should need to have the 2 gallons go in that 4 gallon bucket. And leave the 3 in the 7 gallon bucket.
You could, if there was 5 in the 7, if there was some way to pour out 2, that would do it, but we're not sure how to pour out exactly 2.
Yeah, that's kind of tricky.
It's kind of confusing for me.
It is, especially if you haven't seen them before. This is sort of a, once you're used to them, they get much easier.
I'm with Betty, it's kind of confusing to
Should you
me too.
use like 2 gallon, make it 2 and then 2 gallons and like.
How would we get 2 gallons though? Right now I could get 7 or 4 or 3. 7 by filling up this bucket, 4 by filling up this bucket, and 3 by filling up the big one, pouring most of it into the 4 and looking at what's left. That would give me 3.
Yeah, yeah,
If I could make 2 or 1, those could be useful.
yeah. So yeah, too much would be pretty much useful. If you would fill all 5 gallons in the 7 gallon bucket, yeah, it makes sense. But
Yeah, but there's no lines on the inside to tell me.
yeah, exactly.
Should I just tell you the answer, because it's your first time with this kind of one?
Yeah, go ahead.
Okay, so what they need to do is they fill up the 4 gallon bucket. And they pour it into the 7. So now we have 4 gallons here. Then I fill up, then I fill up the 4 gallon bucket again. And I start pouring it in. And that will make 3 of the gallons go into the 7-gallon bucket.
Okay,
And that means the 4-gallon bucket now
That's
has
one.
1 left. You with me so far?
yeah,
Then I take this full 7-gallon bucket and I pour it back into the well or dump it on the ground or whatever. Then I take the 1 gallon that was sitting in the 4-gallon bucket and put it in the 7-gallon bucket. So that now, and then I fill up the 4-gallon again and put it on top, and now there's 5.
It's-
Okay, now that makes sense.
so you're just
Right.
basically referring as like trickery, a little trickery.
Yes, it's a trick problem. It's not really a arithmetic problem.
Oh, okay.
So if you've never seen them before, now you know how they work.
Okay.
Maybe somebody will ask you one, or you'll see it in the newspaper and you can impress your friends and family.
There you go.
Okay, measurement units. So the history of measurement units is kind of interesting. I wish I knew more than I did, but I've never been able to track down as much information about this as I wanted. So the first thing I want to talk about is an inch. If you were doing carpentry and other crafts like that, in the Middle Ages, you needed a standardized inch, or actually even in the Roman Empire. Because if you made table legs and I made the top of the table, then we wanted the holes I make to fit into your legs and so on, right? So if we all had the same measurement unit, the carpenters could have their pieces fit together. So what people did was they would have a bunch of men get together and hold up their thumbs, and the average thumb width was an inch.
Cool.
And if you had a good group of people, not just 1 or 2, but 20 people do that, then yes, the average inch in your town and the average thumb width in my town, they're gonna be the same.
Yeah.
People's thumbs just work that way, that some people are a little bigger, some people are smaller, but the average will be consistent. So that's what an inch was. A foot was always 12 inches, and that came from the Roman Empire. And very few people have a foot that's 12 inches long, but that's because this was about when you had big clunky boots on. And so that you could walk heel toe, and measure out feet on the ground for planting or something. A yard was different based on where in Europe you were. Sometimes it was the average waist circumference, a belt going around your waist. And sometimes it was elbow to elbow like this. This is called a cubit, like Noah's Ark is measured in cubits. So 2 cubits would be a yard.
Okay.
And then sometimes a yard was just 3 feet, going again by 12 thumb inches. A metric system was invented in France beginning in 1791. And the French Academy of Sciences defined a meter as a 10 millionth of the distance from the equator to the North Pole. So imagine starting at the equator and traveling straight up the globe to the North Pole. But the Earth isn't completely round. So depending on which trip you went, it would be a little different. So they decided it would be the one that goes through Paris, because they were from France. And it was remarkable. The expedition that they sent to measure that distance was off by only a 50th%. So the meter was pretty accurate. And you will see both in the formula sheets and in other things, these conversion factors to help remind you. 12 inches in a foot, 3 feet in a yard, and so on. So the kinds of things you do are convert one measurement unit to another measurement unit. So a problem might be 2.5 feet is how many inches? So I'm gonna pull everyone towards me. And I'm gonna pick on Jody because she's been the most quiet. So these rulers, you can break apart inch by inch. So make a pile of all the inches, just grab one and move it and see how many inches are 2.5 feet. Because this is one ruler of 12 inches, 1 foot, another foot, and then at the bottom, we have 6 inches. That's half of the ruler, right? That's the 2.5, that's the half of the foot extra. Okay, so how many inches is that? Just drag them and count them as you go.
Okay,
30.
You have most not working on that one,
Is 30.
It's 30. That's checked, so 1. That's good enough, you don't have to drag it far.
1,
1, 2. 3, and I'm gonna do all the rest, we're just counting the inches, so these are gonna be up to 12.
okay,
And now keep going with 13. 14,
14,
15.
15. 16,
Mhm,
17,
mhm.
18. 19. 20. 21. 22. 23.
Mhm.
24.
Okay, so what I just did, look up for a moment, I'm interrupting you, 2.5 feet.
Hmm.
Is 2 feet and half a foot. The 2 feet you just finished moving.
Mhm.
We did 12 inches for each of them. With both of them, 12 times 2 is 24.
Mhm.
And then we have the half a foot left, so keep going.
Okay,
Now you're on 25.
26.
25.
25. Okay. 26. 27. 28. 29. 30.
Okay. So it was 30 inches, like Betty said. So we did 2 times 12 is 24, and then we added 6. And we got to 30.
Mhm.
So you can always do these by trying to draw pictures, although that's a little slow.
Mhm.
It's faster to just do 12 times 2 is 24 for the 2 foot part,
Mhm.
and then 6 more for the half a foot part. You could also do 2.5 times 12. Oops, 2.5 times 12 all at once and get 30. If that makes sense.
Yep.
Okay.
Okay, so the moral of the story is when we split a measurement unit apart, the way you were breaking the ruler and splitting it into little pieces,
True.
then we multiply. We do 2.5 times 12 is 30. Now we're gonna go the other way. How many inches? 18 inches is how many feet? So I'm gonna put together 3 inches. I'm gonna put together 6 inches. I'm gonna put together 9 inches. Whoops.
Mhm.
Put together 12 inches, so that's 1 foot. So that's 12 of my 18. And then there's gonna be 13, 14, 15, 16, 17, 18. So whoever made this did it right, there's 18 inches here. And it was 1 foot and half a foot. So the answer for here is going to be, if I have 18. And I divide it by the 12, because 12 inches in a foot. Then I get 1.5. And again, here it would be 18 inches that they gave me. Divide by 12, because 12 switches between inches and feet, and I get 1.5. So when we're grouping something together, you saw me grouping these pieces together to rebuild the rulers, then we divide. So remember those two rules for the GED. If we're splitting something apart, like Jody destroying the ruler, then we multiply. If we are gluing things back together, then we're dividing. Okay, so it's your turn to practice with these. Use a calculator if you want on your computer, use a calculator if you want on the web page. If you have a phone, you can use that calculator.
From my other phone.
And I'm gonna put it in chat if Betty wants to use the website one. Yeah, the link works, okay. So think about for each of these. Are you gonna times 12 or divide by 12? If it's about cups and gallons, then it's times 16 or divide by 16. This picture up here is the reminder about that, if you haven't seen it.
Like, no, that's divided by. Easy.
So Sean moved the 69 inches for A, so he got bigger, he must have multiplied, he did 5.75. So he must have done times 12 to get 69. Okay, 198 inches is how many feet? So if I take 198,
Who's next?
so this is, the first one was times 12, that was breaking apart the feet into inches like Jody did. The second one, we're dividing, that was the gluing together to make feet rulers out of the little inches like I did. So 198 divided by 12 gives me the 16.5, we're on a roll. Okay. How many cups are in 12 gallons? How this picture works is the whole box represents a gallon, like when you're buying a gallon of milk. Half of that would be half a gallon. Some things you buy in half gallons. There's not really a special name for that. A quarter of a gallon is called a quart. That's why we call it a quart. It's a quarter. If I chop my quart in half, then I get pints. And if I chop my pint in half, then I get cups. So you can look at this picture and see, 4 quarts make a gallon, or 1, 2, 3, 4, 5, 6, 7, 8 pints, or 16 cups. That picture is a nice one to help you remember how that looks. Okay, so if we take cups and we're trying to get gallons, then if we have gallons and we're trying to get cups out of it, we're starting with this big thing and shattering it into pieces like Jody did, so we're multiplying. So 12 times 16 for the 16 cups per gallon is the 192, great for that one. Now we're starting with the small thing and gluing them together to make gallons, metaphorically. So now we're dividing, so 40 divided by 16 gave us 2.5, okay.
I guess that one.
Now, all in the GED, it'll also be multiple choice,
Yeah,
so
pretty
some of it
much.
should. Now, ounces to pounds, that's again a 16. Why are there 16 ounces in a pound? Why not 12 like we did with inches?
Well, 12 is by the metal system, 12 pound, and the 16 is by like non-metals.
Sort of, there is something called troy ounces. It's because weights were used on balance scales. And so on a balance scale, it's nice to be able to have half of something. So maybe your computer mouse is half as much as mine, because mine has more junk in it because it's wireless. So you'd put both of yours on one side of the scale and one on the other and they'd balance, right?
Oh,
So if you want to break something into half, 12 you can only break into half once. And then once it's 6 and 6, that's all you can do.
yeah,
Whereas 16 is nice, you can break it in half,
Mhm.
take a bag of grain and put half on each side of the scale and have 8 and 8. And then you can break it in half again and have 4 and 4. And then you can break it in half again and have 2 and 2. And then you can break it in half again and have 1 and 1. So because balance scales were used with weights, but not with distances, that's why they had 16 for the ounces in a pound. Okay, 152 times 16, we're multiplying because we're starting with the big thing, the pounds. And we're breaking them apart, so that's multiplying like Jody did. And then here we're starting with ounces, the little thing, and getting pounds, that's grouping them together like I did. So we're dividing. Okay, hopefully that's gotten it into your brain, you can do your homework. When you're going from a big thing and breaking it apart into little pieces, multiply. When you're starting with the pieces and joining them together, then you divide.
yeah, oh, okay, yeah, now we're back to the same thing we already have.
Yeah, and this might help you or might not, so.
Reminder.
Yeah, there's some shattering and grouping and things like that. But I don't wanna really talk about this now because we just did a good thing and it's working, so let's not mess it up.
Mhm.
Sounds
But at
good.
home, if this helps you, you can look at that one.
Yeah,
Okay, so we did both the measurement and the first part of geometry. Let's just do a preview of what's happening next, not counting the warm-ups. So our next thing is about circles. In class on Tuesday, I will bring string and we're gonna wrap string around our shoulder, or not shoulder, our bicep and our head and talk about how circles work. There's this cool image that has pi, and it takes a circle and rolls it. And you can see how big the outside of the circle is as it kind of unwinds. So that red string is unwinding off the wheel,
Mhm.
so we'll talk about that more.
that's your circle.
And then we'll talk about how big the area of a circle is.
Oh,
Because
yes.
today we were using paper rectangles, everything was at its
Mhm.
core based on paper rectangles. But you can't really do that with circles, there's no rectangle, you can like draw a box around it like we do here,
Yeah.
but it's more complicated, so we'll
Mhm.
do that more complicated. And then we'll do one to make sure we understand it.
Oh, yeah.
And then the last part of geometry is angles. So we're gonna talk about when you turn, how do you measure how much you're turning?
Yeah.
So that's what this one is about. On the homework. Now you should be able to do all the homework on using data. You could do most of it already, but now you can do the measurement as well as the averages and probability from last time.
Yeah,
And for geometry, how did they break it up? You can do angles. No, not yet. We haven't done angles.
Yeah,
Can you
not
do
yet.
polygons? Yes, that's the one we did. Can you do circles? No, not yet.
not yet.
But this polygons one we can do. So why don't I actually just make it be first? So that's
Yeah,
easy.
rearranging it.
Yeah, let me rearrange it so that it's first. So that one.
Moved it.
No, I didn't move it. I thought I moved it.
You.
Let's try this again. Where's that? Something was wrong. There we go. Moodle sometimes just doesn't work right. It's not-
There you go, moved it in front of it.
Okay, now polygon's the front, so you can do the first one, don't try the other two yet, unless you
Okay.
already know it from some other class. And remember, if you want this formula sheet, where did we get that? We went to the welcome and syllabus, where all sorts of good stuff is. And one of these is named GED info. And then the GED info, the formula sheet is right there.
Cool.
Oh,
So when I get home or in the morning, the reporting for today, I'll have to put in both the using data and geometry. I'll put the link in both places.
Alright,
And if you want to do the Math C readiness check already, you can start. It has my open math section, and now we fixed it, so it's there.
okay.
okay.
Okay. I'm gonna stop recording.